We are back once again, fellow LeetCode extraordinaires. This is day 66 of daily LeetCode. So, yeah, yesterday was a good session. We got to use the new ADM BFS, the new BFS from the ADM. Very, very cool algorithm. And then we got to augment it to use or prepare it to be used with a level, right? So there are three functions we can kind of sneak in there: process vertex early, late, and edge. Right, and then we found a way to add process level. So hopefully this serves as the foundation for, hopefully it serves as a foundation for us to be able to, I guess, generalize this approach to many problems. That being said, day 66. So I guess other interesting things, right? The system design aspect, right? So LeetCode is pretty binary, right? It's also pretty creative, but the output is pretty binary, right? So you do a problem, right? You get a big green screen, right? Just something that just your brain rushes with dopamine when, at least for me, when I see the green success sign, there's just something about the dopamine that just hits your brain, right? So that's pretty cool, right? It's a lot more binary, right? It's pass, fail, right? And even though you can get a slow solution, at least you know, like, you still kind of met the border for pass, fail. System design is less so that way, right? Because there's not really I mean, if you have like a system design part of it, like a problem or an interview or something, it's like, it's hard to really know, right? It's hard to really know, right? If your answer is like good or bad, right? I mean, it's like a scale basically. So it's very interpretive, right? And while I think there are like ways to sort of objectively measure like whether design is good or not, it also ultimately depends on the use case, right? And so when you're doing like the prep problems, like design Twitter or design something else, it's kind of hard to know, right, without someone else like doing it with you, whether or not you're doing well. So just interesting and tough, right? But I noticed that with at least reading about the system design has been pretty fun. Yesterday we read about, I think, Etsy's blue-green testing, which was pretty cool. Their Code as Craft blog is pretty cool, but I wish they had a few more posts about like their infrastructure and / platform design. I started reading earlier again today. Oh yeah, so today we're also reading a ton about Memcache. Yeah, and something that's just fun about system design. System design may low-key be a W topic. When I first started, I was like, oh, I don't know. But I guess that's the thing, right? Maybe we like the things that we think we can be good at. Because when I didn't understand system design at all, I thought it was torture. But now that I'm starting to get it, it's kind of fun, right? And I guess that would be similar with programming. Programming is a lot more fun or I guess things seem like a lot more fun when you feel like you're getting better at it. So that being the case, engineering blogs for companies are actually pretty hype, right? So W content, right? So yeah, hopefully we can look at some more engineering blogs. I was trying to look through eBay, but there's just a lot of other blog posts where I want like more system design, but each one is kind of diving into a specific topic, which I guess is still important. But yeah, we kind of went through a rabbit hole of Memcached and Memcache. Now I'm realizing, right, what Redis and Memcached are, so that is pretty dope, right? So yeah, system design is kind of low-key a W, right? So I wonder if there's a platform where you can practice system design. Like you can pay someone to just be like, hey, work through this system design with me and let's work through the edge cases and stuff like that. And the designs and the trade-offs, that would be cool. I think Interview.io has something similar. So I guess you could do like a system design interview. Those interviews are expensive though. So it's tough. It is tough. But I guess people's time, the people who have a lot of system design experience, I guess you want to compensate them fairly. So that is difficult. That's a difficult problem to solve. Either way, we're only about, we started system design 4 days ago. So we're only about, this would be day 5, or no, day 4. Today would be day 4, day 5 of system design, right? 30 minutes a day. So it's really like it's really like maybe 2.5 hours I've been into it. But each day, you take the time between, right? Hopefully more falls in. So yeah, system design, low-key, is a W. I'm curious to see, right, just thinking about LeetCode, I wonder how their system design works. That is besides the point. Either way, right, I think there are some changes coming to the channel, right? Ideally, I'm going to be on vacation the next few days, but the grind does not stop. So it must continue nonetheless. So I will be doing LeetCode the same amount of time, right? Every single day, right? Rain, sleet, or snow, uphill both ways. So that will be the goal, right? I'm hopefully going to try to get them up early. So yeah, yesterday's came out pretty late as well, because a late session, right? It takes about an hour and a half to upload the videos. So my internet is pretty slow, and then YouTube has to process the video to make sure there's no like I don't know what they're processing, but maybe advertising content and stuff. That takes like an extra hour and a half to 2 hours. So by the time I start a video, right, it comes out pretty much 4 to 5 hours later. So it's kind of or I'll say if I upload it right after I'm done. But yeah, that being the case, system design is an absolute W, right? I'm thinking hopefully there could be a cool system design service, or maybe one that's cheaper in the future, or maybe there could be a platform for system design. That would be pretty cool, right? Maybe there is a way to do that, but it's always so general, right? But maybe if someone could create some kind of graph structure or LeetCode style. But I think LeetCode actually does have system design sort of problems. Maybe it's just not included with our, yeah, I think it's just, I thought they did. I think they do. I don't know where it is, but I'm pretty sure they have system design problems. Maybe if we go to explore. Yeah, so they do. And I think this is still kind of general though. So it's less binary, but either way, right? I'm going to do a session today. It's going to be approximately, it depends. It could be anywhere from 30 to 45 minutes to an hour, right? I have to pretty much go to sleep for like 7 or 8 hours. So it's really going to depend. So yes, I'm not really sure exactly how long we want to go. At minimum, we're going to do 30 minutes, right? But I'm just trying to make sure we manage things so that we still have some brain juice left over. Right, so let's just start with 45 minutes to start, and then we'll see how far we get. So we're going to jump into it, but at the same time, don't forget to join the Hyperbolic Coding Chamber. This is a legendary coding chamber that has millions of people joining daily to learn, right, to pretty much push forth their educational prowess, right? So you're going to want to join. Lots of cheat codes, right? There's even a command you can type into any modern IDE, and it's going to actually spawn an instance of GPT-3 and solve the problem for you. So you're going to want to be able to know that cheat code. So yeah, that cheat code is in the Discord, and this is actually true. So yeah, so we're going to jump into it. Make sure you join the Discord. This is day 66, right? And we're going to start with some problems. And yes. Invert binary tree. We've done this one a few times, right? So pretty much the inverting a binary tree is swapping the left and right nodes for every node in the tree, including the root node, and it produces an output that looks like this, right? And there's no follow-up. It looks like the nodes in the tree can be up to 0, right? So if that is the case, then we're probably going to want an if block, right, to avoid that happening, right? Avoid us working on an empty array. But I think the best way we can go about this problem is likely with a DFS, right? Or is it? No, maybe with a BFS actually. We had 4, we could swap 2 and 7, right? Then we get 1 and 3, we could swap these. 7, then we would swap these, right? So I'm thinking a BFS might actually be the best way to go about this. So we'd have 4 on the queue, right? We'd swap its nodes and then push its children on, then swap its children, push its children on, right? So I think that could be a method to solve it. So we'll say, we'll just do a BFS, right? Swapping children nodes per node, right? And like we mentioned, the root could be empty, right? And they want us to return the same root, right? So if the root is empty, we're going to return root, which should also be null. From here, we can start our BFS with our root node within it, and we'll say while the queue isn't empty, right? And at the end, we're going to want to return the root, right? Well, while the queue isn't empty, right? And the queue isn't empty, right? We're going to want to get our current node, so we're going to pull that off of the queue, right? And we're going to want to make sure that this node exists, right? Now, if cur exists, we're going to want to swap its children. Swap its children, we're going to need a temporary array, a temporary data store, right? And here we're going to say cur.left, right? Since we're saving cur.left, we're going to set cur.left equal to cur.right. Then here we can actually set cur.right equal to temp. So we save left, we overwrite left with right, and then we overwrite right with temp. From here, right, if cur.left exists, we're going to want to push it as a child onto we're going to want to push it onto the end of the queue. That way, we know that we can process the next child, basically. And then we can swap its children and so on. So then we could push on cur.left. Then from here, we could do cur.right, then push on cur.right. Before we run it, probably makes sense to see if this makes sense. So we push 4 onto the queue, we pull off 4, right? 4 does exist. We'll swap 7 and 2, and then push 7 and 2, right, onto the queue. Now that we've pushed it onto the queue, we're going to pull 7 off of the queue, actually, because we swapped them. So we're going to pull 7 we're going to push 7 onto the queue and push 2 as well, which means the next one we pull off the queue will be 7, right? 7 does exist. We're going to swap 9 and 6, right, and then push 9 and 6 onto the queue. Right, now we're going to process 2. We're going to swap 3 and 1, right? But 9 and so now we're going to have 9, 6, 3, 1 remaining. 9 exists, right? We swap its children, but both of its children are null. So we actually don't do anything, so we don't push anything onto the queue to swap. So I think this makes sense. Let's try it for our first case. Okay, let's try it for our submission. So this makes sense, and our time complexity here, since a BFS typically operates in O of n plus m time, so we're going to be linear time over the entire tree, as well as linear space in the worst case, since we're going to have at most n elements in the queue, in the worst case. So here we have square root of x, given a non-negative integer x, which means positive, so x is going to be positive, right, or 0, compute and return the square root of x. Interesting. Square root of x. Since the return type is an integer, the decimal digits are truncated. Only the integer part of the result is returned. So we only want the integer of the square root and not the actual decimal value. Of the decimal value, right? So you're not allowed to use any built-in exponent function or operators such as pow of x to 0.5, right? Because the x to the 0.5 is the same as square root, and x times, and this is also x to the 0.5 as well. So given x, right, which is 4, we want to find the square root, right, which is 2. And given the square root of x, x, which is 8, find the square root of 8. This is going to give us 2.82842, but the actual value is going to be 2, right? And it seems that x can actually be equivalent to 0. So I think there's 2 approaches to this, right? If we want to find and compute the square root of x, what we're really looking for is a number, right, n, such that n times n equals x. right? If that's what we're looking for, then we could phrase this problem as a linear search, right? Because our search space, a linear search over the search space of 0 going to x. So if we searched all the values of 0 going to x, and we did 0 times 0, and then 1 times 1, and then 2 times 2, and then 3 times 3, right? This would allow us to find the exact square root. But the problem would be that when we want to find something like 8, if we did 2 times 2, we get 4, then 3 times 3, we'd get 9, which means that when we go past the number, we want to return the number minus 1. So I think we could implement that. So we could do O of n, right? And this would be constant space as well. And the goal would be to pretty much do a linear search over the search space, right? So if that's the case, what's the best way to go about this? You could do a for loop, right, with I equal to 0, I is less than x, I plus plus, right? What we could say is if I times I equals x, then we found the perfect square root, right? We can return I. But I'm also thinking there's one more thing we want to check, right? If x is 1, if x is 1, right, is there a square root, which is there a value which multiplied by 1? If the value, if x is 0, right, is there a square root of, is there a number that you can multiply by 2 to get 0? No. Right, and if x is 1, is there a number you can multiply by itself to get 1? You can do 1 times 1. So I think what we're going to want to do, right, is say if x is less than or equal to 1, we want to return x, right? And this is just going to save us some time. And then we can actually start I at 2 here, right? And then we can have another case, right? If I times I is greater than x, right? So in the case we're looking for x is equal to 8, right? We do 2 times 2, which gives us 4, then 3 times 3, which gives us 9. So we'd be at 3, which gives us the first number, which is greater than x, which means that the value we're looking for is actually behind us, right? So we could return I minus 1. Now, what should we return when no such value exists? This is unknown, right? Maybe we return 0. Try it for our first case. Let's see. Interesting. So our input is x, right? When x is equal to 2. Oh, right. So maybe we actually want to start this at 1. So that actually does make more sense, right? And if we run this for 2, we still get 0. So that's strange. So if we did 1 times 1, we don't get 2. If we do 2 times 2, it should be greater than x. So then we should return I minus 1. I see. So if we start at 1, right. So right, with this case, we want to make sure we do less than or equal to x. So we'd be good there. Okay, so this works. This would be linear time, right, where pretty much the number of operations we do in the worst case will be x. So if our value is x, right, we're going to perform x operations, which can be a lot, but we can actually do this faster, right, because our search space is ordered, right? So for the values, right, if we say that, you know, v sub, right, let's just say we have these values, right? We'll say v is the values between 0, or I guess 1 and x, right? All these values are ordered, right? 3, 4, 5, 6, X, right? Which means that since our search space is already ordered, we can speed this up with a binary search, right? So we could calculate a pivot, right? And if our pivot squared, right, is equal to our value, then that's great. And if it's not, right, there's two cases. If it's greater than if it's greater than X, right, so 5 squared, let's just say we're looking for 8, something simpler, right? If we calculated 5, right, let's say the number we think we're given is 36, right? Well, we know that 5 squared is 25. So if 5 squared is 25, there's no reason for us to check 1 through 4 here, right? Let me see how small this is. So it's actually a little bit small. There's no reason. Yeah, there's no reason for us to this way. I think this is better. There's no reason for us to even consider the range 1 to 4. The new range would be 5 going to X, right? Similarly, if we were searching, let's say X was 25, right? And we're at calculated pivot, and maybe it's like 7, right? 7 squared is 49, which means there's no reason for us to even check, you know, all the values going up to X, which would be like, you know, 8, 9, 10, 12, ... 36. So you can skip all those values. So this would actually give us log of n time. This would actually be much better outcome. So to implement this, right, we're going to need 2 values, right? Left, which is going to be our left boundary starting at 1, and right, which is going to be our right boundary starting at X, right? We're going to want to change this to be a while loop, right, while left is less than right. So while they haven't passed each other, right, or they're equal to each other, then we still want to consider it. We still want to consider this boundary. Once they pass each other, right, the boundaries are invalid, right? And so we'll have a similar thing that we had before, right? If we say, now we're going to wonder what I is, right? Well, to get I, we're actually going to have to calculate our pivot. The pivot is going to be the value directly in the center. In the case when the elements are even, the range is odd, I mean. It's going to be the center when the range is odd, and the element leaning to the left, right, when our range is even. Calculate our pivot, we can do math, we can do left plus the math.floor of right minus left over 2, right? That will give us our pivot. Now that we have our pivot, we can actually just call this I just to be a bit more, or we can just call it mid to be a bit more descriptive. Mid times mid equals X, right? Then we want to return mid. But if mid times mid is greater than X, right, then this is where we're going to do our shrinking of this boundary or this window. So if mid times mid is greater than X, right, then our new right point, we're just going to shrink it, right? So if mid times mid is greater than X, right, then that means our newest portion where we can move right up to, or we can still consider all valid elements, is going to be mid minus 1. The reason it's going to be minus 1 is because we just processed mid. So if we set it equal to mid, we end up eventually processing mid twice. So we want to process an element we haven't touched before. And the same thing, right? If mid times mid is less than X, right, then we want to move left equal to mid plus 1. At the end here, I think we're going to have some special cases, right? For example, if we consider an input that looks like this, right? X equals if X equals 8, right? And let's just say this is how our mid would start, right? It'd be between 1 and 8, right? 8 minus 1 is 7, over 2 is 3.5, floor is 3, plus left, which is 1, is equal to 4, right? 4 is less than 8, right? So our left is now going to be 4 plus 1, right? and our right is still going to be 8. Wait a second. I messed up. 4 squared is 16, which is greater. 4 squared is 16, which is greater than x, which means we're going to set right equal to mid minus 1, right, which is going to be 3, right? So now we're going to calculate a new mid, right? It's going to be right minus left. So 3 minus 1 is 2 over 2 is 1 plus left, which is 1, right, gives us 2, right? So our new mid is going to be 2, right? Now if we do 2 squared, does it equal 8? No. If we do 2 squared, is it greater than 8? No, right? If we do 2 squared, is it less than 8? It is. So left equal mid plus 1, right? So now left is actually going to equal to 2, right? Now we're going to do another check, right? Because left is still less than right. We'll do right minus left. 3 minus 2 is 1, right? Over 2 is 0.5, floor is 0, plus left, which is 2. I think I messed up. The left one should have been left plus 1, which would have been 3. No, this was 1, right? Then it turns to 2, right? We know 2 doesn't give us the value we need because it's too small. Then we take this to 3. Once we take it to 3, right, then we'll know that mid times mid, right, is 9, which is greater than x. So we do left plus equals 1, which takes left actually to 4, right? And this is going to stop our loop. But the actual value we're looking for is going to be 2. So we can actually return right minus 1 in that case. So let's try it. This is all over the place. So we have your input, which is 2. So this does work. Interesting. Returning right. I was led to, for some reason I thought I was going to have to subtract 1. For some reason we don't have to. So we still have one more iteration. Just curious, if we swap the place of these, does this still work? It still works. Interesting. It should be log of n time, but it was kind of slow. So here we have 3 sum. Given an integer array nums, return all the triplets such that num sub I, num sub j, num sub k, such that I does not equal j, I does not equal k, and j does not equal k, and nums I, j, and k equals 0. So they want the individual numbers we use to sum to 0 to be completely distinct, right? But they have to sum to 0, and we want a solution set which must not contain duplicate triplets. Right, the only possible triplet does not sum up to 0. The only possible triplet sums up to 0. Notice that the solution set must not contain duplicate triplets. So this is interesting. We know a method, right? So we know a method to find the target number, right, given a sorted input. Right, so to sum with a sorted input, we can find numbers that sum up to a particular value in linear time with constant space. Requires sorting though. Our input is not guaranteed to be sorted, so we probably want a method which works agnostic of that. Right, and one method that works is a map-based method. And I think this map-based method So we know we have a method for to sum, right, that we can do. And I'm trying to think if I should call it since we're a bit short on time. We did 45. No, we have 5 minutes left. So let's see if we can do this in 5 minutes. We have this array here, right? And we want a version of to sum such that, right, if we give it a, so basically the reason why we can use a version of to sum, right? We know that we have an algorithm for to sum, which can give us 2 elements that sum up to a particular number, right? So all we need to do, right, is do 0 minus our current number, right? 0 minus our current number, which would give us -1. Then we can just run to sum with our goal being -1. So the way this to sum algorithm would work we actually don't have, I'm actually not certain that we need to worry about it being sorted now. If we look a bit closer, right, if we start with a given number -1, right, I have 0 here, I have left and right. Now, do these numbers sum up to 0? No. Right, so we move left over. Do these numbers sum up to 0? No. Do these numbers sum up to 0? No, no, no. So we go to 0. Can we find a number that sums up to 0, right? These 1, -1, and -4. So we had 0, 1, and -1, which makes sense, right? There wouldn't be any more here, I believe. Then we could go to 1, right? Do any of these sum up to 0? no, we go to this negative, right, and there'd be no more, we sum up to 0. So I think we could still do it even though it's unsorted, right? But there's one thing we have to make sure. We want to make sure that our solution set must not contain duplicate triplets. One way we can do that is make certain wait, actually, now that I'm thinking about it, we can sort our solution set because we want to make sure that we just have to make sure that I, j, and k are different indices, which is fine. And the way that we're deduplicating, we're just going to make sure that the indices we used are different. So we can sort our array. Right, we remove -4 here. We add another -1 to the front. Right, and we remove this one from the back. Right, then we can start -1 as our start. Right, do an iteration over this subsection right here. Right, to get all the values that sum up to 0. Right, and then the other thing we're just going to want to do is skip. Right, to prevent duplicates. Right, we know that if we have -1 here, right, that we can get 0 by adding 0 and 1. We have another -1 here, so we can do the same thing. We'll have a duplicate triplet by processing this number again. So we want to skip values that are the same. This should help us prevent duplicates. So we could sort input. We have a little bit of time left. We sort our input. If we sort our input, right, then we can use our linear time constant space two-sum algorithm, right, for a particular target index, right? So we're going to iterate over indices. Right, we're going to want to make sure, right, that nums sub I does not equal nums sub I minus 1. And that's important so that we skip creating duplicates. Right. And then we can have this said two-sum function, right? Return an array of triplets, right? Returns an array of triplets, right? Push two-sum output to push two-sum output, or add two-sum output, right? And then we can return output. There's one more problem though, and that problem is with our two-sum function, because our two-sum function has the potential to create duplicates. Right, because it wants to find all pairs for a particular source index, like -1. It wants to find all pairs that sum up to 0. To do that, right, it could start at -1, right, with 2 at the end, and okay, right, this would equal 0, right, -1 plus -1 plus 2. But now imagine after it finds 0, right, it moves left up, right, and it won't find another duplicate, right? But imagine if we had something like this. Right, now after we process this index, right, this will be our source index. Our start would be this -1 going to 2. We'll find that these three do equal 0, right? And then these three, right, this -1, and 2 also equal 0. And this is a problem because they don't want any duplicate triplets, right? So we can't have two sets of triplets that use the same numbers to equal 0. So this is what they're saying with this explanation. -1 plus 0 plus 1 equals 0. -1 plus 1 plus 0 also equals 0. But the output is actually 2 tuples and not 3 tuples. So we're going to want this same skipping mechanism in our two-sum implementation as well. So we can jump into implementing this. Right, so we'll say nums.sort, right, with a comma b. We'll sort it in ascending order. Then we're going to want to iterate over the indices, right? We'll say let I, do we need actually, yeah, we do need access to the indices. Let I equal 0. I is less than nums dot length I plus plus, right? And from here, what we're going to see right? So if num sub I is not equal to num sub I minus 1, then we'll be in business, right? And this actually works with our first indice as well, because -1 will not equal undefined, since I minus 1 is going to give us undefined, right? Then we're going to want to make sure, right, that triplets is going to be equal to 2sum, right? We're going to need probably a source index to start, right? And access to the nums array. And then we're also going to have this output array, right? We don't want to add empty triplets, right? Because there are scenarios where there's no triplets, right? So we'll say if triplets dot length does not equal 0, right? Then we'll just do output dot push triplets. Part of me thinks we need to copy this array, but now we're going to have 2sum, right, which takes a source IDX. We'll just call it source, which is going to be a number, and then the array of numbers, it's going to return an array of numbers, right, and we'll call this triplets. This is ultimately what it's going to return. See, okay, we're still recording, right? And so this version works similarly to like the binary search we just implemented earlier. It's going to shift up and down, right? So our left, right, our left boundary is actually going to be source plus 1, right, with our right boundary actually starting at nums.length minus 1, which is the last element in the array. While left is less than right, right, then we're going to want to do some work. The work that's there, right, we're going to have to calculate our sum. So our sum is going to be equal to num sub source, our source index, right, plus num sub left plus nums sub right. Now, if this sum equals 0, right, then that's awesome. We now have a group of numbers that is actually equal to 0, a triplet, right, that we wanted. So to do that, to keep this number, we can actually just do triplets dot push nums sub source, nums sub left, nums sub right, right? And then like we said earlier, we're going to want to implement the same thing we had earlier down here, right? So after we add that number, we're going to want to skip creating any potential duplicates, right? So we can change this to a while. And then we can also say, right, that num sub I is going to change to left and does not equal left minus 1, right? And left is less than right. And we're going to do left plus equal 1 to skip those values, right? That would give us potential duplicates, right? And if it doesn't equal 0, right? So we can make this a little bit smaller so it's readable. If the value doesn't equal 0, right, then we basically want to ignore it. So the value doesn't equal 0, right, then we're going to want to do left plus equal 1. And the reason we added this left plus equal 1 before here is because this is a typical thing you have to do, right before a while loop that you're expecting to increment that same counter, right? If we found a triplet without this line here, this loop would run basically forever in a particular circumstance, right? Because while left is less than right and num sub left is not equal to num sub left minus 1. If they were the same, or if they weren't the same, all right, so if they were the same, this would run forever, right? So if they were the same, and I'm actually realizing I actually want this to be equal. So if they are the same, right? If they are the same, then we're going to keep doing left plus equals 1. Now, if they aren't the same, right? For example, 0 and 1, this loop would run forever, right? Because if they aren't the same, we never left plus equals 1. Then we'd calculate our sum again, it would equal 0, we'd add it, right? But then they'd be the same, right? So then we'd go forward. So that's why we need this left plus equals 1 here. And so I feel good about this. Let's try it. Looks like we have some arrays sticking out. Output is none. I'm thinking that's because you probably want to now we actually have values in here. We're missing another value. I wonder if this is because we need to copy this. That seems strange though. This one always takes a bit of debugging. For some reason when I print the array, there's an issue. Or now there's always an issue. Oh, I forgot I added this. Negative. So presumably if we get to -1, right, we'd produce a triplet where -1 and 2 gives us a value, right? But also we'd go left plus equal 1, right? And they wouldn't be the same. So we ideally should have this triplet as well, but we don't. I think I'm seeing the problem. We're doing left plus equal 1. We want to move this forward only if so -1, right? -1 here. We would say, okay, is left, right, equal to negative, is left, right, which would be -1 here. Is it, we do plus equal 1. Now is 0 equal to 1? No. I think I'm realizing this is a weird way of doing it. This was not exactly the two-sum algorithm which generates what we're looking for, right? the way that one works is by shifting left and right, depending on the circumstance. That's why it's sorted. So if we already have sum declared, right, what if we say if our sum is less than 0, right, then we'd like to do left plus equal 1. Yeah, I'm pretty sure this is going to work, but the way we know it's going to work, this one I'm realizing, I think I need a, yeah, we know this, yeah, so I think this one is one of those ones where I think I just need to, I'll make a note, next time I do this one, I need to actually sit down and make sure I know what's going on, because this one I think I'm definitely, I would say this is the first problem I think I've ever regurgitated. Right, I generally understand the principles, but not that well. So this one ends up with a bunch of errors. I think it's because I know the code that's supposed to go there, but I don't necessarily. I also understand it as well. Yeah, I'm not really sure what went wrong here. I think it's just one of those days where my mind is messy. So we literally just wrote if sum equals 0, right, and then tried to write a sillier algorithm. Right, but that's not even the original algorithm we wrote wasn't even the two-sum algorithm. I think it's just one of those days where we're just going too fast. So that being the case, we'll count it next time. Hopefully we'll struggle even more. But that's a wrap on day 66. I'll see you soon.